Okay, yeah, thank you for the introduction. This is work with Akira, Donghook, Dylan, Anna, Trevor, and Marcus from UC Berkeley, Sony, and Max Planck Institute. So today I want to tell you about the new compact bilinear pooling method we use to combine questions and image representations to both predict the spatial attention and then also to predict the answer. As you know, there's lots of language and vision tasks in our field, and one is description, where we want to describe the image or scene with a sentence. But if I want a robot, for example, to give me the bowl with a brown sauce, I want it to locate it and then probably to pick it up. But if I even don't know what this brown sauce is, I might ask, what is the brown sauce? And hopefully the robot can tell me that this is gravy. And what does it have to do for that? Well, first it has to locate the gravy or the sauce and then answer, sort of describe this region with gravy. And let me tell you how we approach that. By first asking, well, how can we actually combine this visual representation and the language representation? And well, if we use our favorite CNN for the image and an LSTM or any other recurrent network for the question, we get some kind of semantic representation which hopefully has the most important elements of the question represented, such as spoon, plate, and so on for the image, and is there and feast and so on for the question. And to now answer the question, we want to ideally find out, well, what is feast relating to in the image? And well, it's probably relating to plate, bowl, and food, and so on. And ideally, this is sort of, or we can think of that as being some kind of attention missing or like a multiplicative interaction, because if we multiply feast with all of these different things, such as plate, bowl, food, we would be already there and can easily answer the question. So ideally, we want to have a element multiplicative interaction, but also allow all elements to interact. So let's look what other people did, or most other people did. On the one hand, people concatenate representations, and this is great because all elements can interact, but the interaction isn't multiplicative, so in this case it will be hard to learn the output classification. There's also the technique of just multiply element-wise multiplication, which is also good because it has multiplicative interaction, but not all elements can interact. And because we have to really match the elements up, that means it's difficult to learn the input embedding. So what we suggest is to take the outer product of two vectors, or bilinear pooling, as, for example, recently has been shown for bird classification by Lin et al. To work very well in the single modal case. This is great, but actually it has lots of parameters. If you do the take product and have large feature vectors, you get like millions of parameters or billions even, depending on the size. So we have high number of activations and high number of parameters. Luckily, at the CVPR, a colleague from our group, Yang Gao et al., presented compact bilinear pooling, which compresses this outer product to a much more compact representation. So let me walk through how we do that for the multimodal case for our scenario here. So we have the outer product, and then we can take an approximation or a random projection, and we use the count sketch to compress that. And that's already good because this reduces significantly the number of parameters we have to compute or learn. But we still have a large number of activations and high computation because we have to explicitly compute the outer product. But Fang and Pa have shown that actually the count sketch of the outer product is equal to the count sketch of X and then convolved by the count sketch of Y. So we can actually simplify this to just first doing the count sketch and then doing a convolution. And we can further optimize that by doing, instead of a convolution, the element-wise product in FFT space or frequency space. I just want to note that the work from Adele, and which also participated in the challenge, actually have like some similar idea in the sense that they also have multiplicative interactions, but they use a different approach to it by predicting the network layout with the question embedding network. So how does now our network look like? We have we extract resonant features on 448 times 438 images, encode them, and we have a similar pipeline as other approaches. On the language side, we use two-layer LSTM and a learned embedding, and we feed both of that in the multimodal compact bilinear, which then is normalized and used to predict the answer. The first results we report by training on train, validating on val, and doing the test on testDef. And here we see several of the ablations. So we compare with element-wise sum, coordination, adding multiple fully connected layers to, and which leads to the same number of parameters. And we see that multimodal compact bilinear achieves the best performance. We also compare to the full bilinear model. Here we reduced the number of input dimensions because it wouldn't fit in memory and we couldn't learn it. So here we see that multimodal compact bilinear is actually a good approximation for the full bilinear. Okay, now I motivated at the beginning that we want to answer this question: what is the brown source, which required some sort of localization or attention. So I'll hand over to Akira to now tell you how we did this attention part.
Thank you, Marcus, for introducing. I'm Akira. So here, I will explain how we use MCV to predict spatial attentions, and then MCV again to predict the answer. We are using MCV twice. Here, we have the output of Res5C, and here, we tile the output of LSTMs to match the shape of the Res5C. And then we apply MCV across each spatial location and create this MCV representation. From this MCV representation, we use two convolutions to create the attention mask. And we generate the final attention feature by applying a weighted sum over Res5C representation and the attention mask. Okay. Here, then the attention feature is again combined with the question representation through another MCV and get the final answer prediction. This is an actual example of our attention system. Is this person wearing a hat? And we can see that the system is somehow attending around the person's head. Here we observed the advantage of MCV over concatenation. These results show that the advantage gets even better, especially with attention. Using only MCV already gives us 1.4% boost, while adding attention gives us 4.1% boost, which is the largest improvement we got throughout our work. In this slide, we have the final two numbers we submitted to the challenge. Other than MCV, we used two techniques to improve the performance. The first is we used visual genome dataset for training. And with this dataset, we got additional 1 million question-answer pairs. And as you can see in the figure, we got about a % boost with this additional data. Second, we ensembled several models by averaging the activation before the softmax. And then we got another 1.6%, up to 66.7%, and this is the final model we submitted to the challenge. Finally, we also used the exactly same model for the multiple choice challenge. And the only difference is we restricted the prediction with the given answer candidates. And we got 17.2% for the multiple choice challenge. And after getting these results in VQA, we were interested in how MCB performs on other tasks. For the Visual 7W dataset, which is a multiple choice VQA dataset, we additionally embedded the multiple choice answers and combined with the third MCB to choose the answer. We also evaluated on grounding task, and in both cases, we observed that MCB outperforms the multimodal methods. Here we have some examples. What is the woman feeding the giraffe? We can see that the system is exactly attending to the carrot and answering carrot. And what is the hairstyle for the picture? The system attends to around the head and answers ponytail. This is a failure case. What color is the chain on the red dress? It is looking at the chain but answers pink. We have a bunch of examples, but maybe we're running out of time. So we have 3 takeaways from this challenge. The first is we looked at the interaction of 2 modalities with the compact bilinear representation. We found that MCB is a powerful method to combine visual and language representations. And second, we succeeded in predicting spatial attention with MCB. In fact, using the MCB to generate attention gave us the largest jump throughout our work. And third, we would finally like to emphasize the generalization capacity of our model. Experiments shows us that MCB can be effective in other VQA datasets like Visual 7W and also in grounding task. So I believe our multimodal compact bilinear model can be also beneficial for other VQA models. Okay, so please come to our poster session, and we have a demo in that link. So please have a look there, and the call will be available soon. Thank you for your attention.